So welcome back to the second part of today's course session, where we are going to explore in more detail the world of infinite sets. We've already seen a few examples of the weird things that can happen when you move from the finite to the infinite. Now you may ask yourself, okay, sort of what does this have all to do with the motivating question that we had? Namely, can we program a computer with an unbounded amount of memory to print out any possible real number? And the answer will be revealed in the second part of the lecture. Before I forget, I've been asked to remind you that as of today, you can submit your evaluations, teaching evaluations. So I've been asked to tell you that you should do so, and I've done that. Okay, so I'm even on record on YouTube as saying that I reminded you. So do it. Second thing, tomorrow you will receive an exit questionnaire from the Automata Tutor guys. Even though we're still going to use it, but anyway, sort of the exit questionnaires is only about the NFA part, which is the part that is currently under test from you and from us. Okay, so please answer. They're doing a great job for us. They are helping us, we are helping them, and the exit questionnaire will be a good thing for them to get more input so that future generations of students can use the tool to the best that the tool can offer them. Okay? So, Loris, I did it. Okay, I'm just talking to somebody who's not listening, but that's a standard thing. That's what you get used to when you are a university lecturer. You tend to talk often to people who are not listening, and at the same time, this is what people tell me when they're talking to me. So I know I know how it feels, both ways. Okay, so countably infinite sets. Let me give you another example of a countably infinite set. And this is a set, the type of set that you've been working on since the beginning of this course, namely the collection of all strings over a non-empty alphabet. This means you have at least one letter that you can use to write strings. If you have no letters, then you can only use one string, so you can only write one string, the empty string, everything is boring. But as soon as you have one letter, then you can write infinitely many strings. If you have the letter A, you can write the empty string, A, 2 A's, 3 A's, 4 A's, 5 A's, and I think you can guess the follow-up story. Now, if you only have the letter A, then if you write the empty string, that corresponds to 0. If you write A, that corresponds to 1. If you write AA, that corresponds to 2. If you write AN, n A's in a row, that corresponds to the number n. You're actually writing numbers in unary notation. So when you have only one symbol, it's absolutely unsurprising that what you have in sigma star is a countably infinite set, because you're just writing numbers as strings of only one symbol. This is like when our ancestors, they had to count how many sheep they had. And what is it that they did? Perhaps they had a little stone per sheep. And the sequence of stones would tell them how many sheep they had. And of course, instead of sheep, you can substitute the number of enemies that you killed or whatever else you wanted to count. Billy the Kid probably had sort of on his belt, he would put tack one with his knife. He would just make one mark every time he killed somebody. I don't know whether it's true, but it sounds good anyway. You're counting in unary. Well, but what if you have more than one symbol that you can write your strings with? Do things change? Suppose that instead of A, you have ABC or the ASCII alphabet or any finite alphabet. Well, this doesn't change anything. You can still write a countably infinite set of strings. You can still enumerate all the strings that you can write. And how do you do it? Well, by following essentially the same strategy that people used to follow when, or roughly, morally, the same strategy that people used to follow when they were putting together those big volumes called the phone books. Remember those? Probably you haven't seen one, but I have. Yeah, well, I'm sure that some of you have seen them as door stoppers, used as door stoppers or something like that. So you basically take all the strings that you can write using your alphabet and you order them in some way. Now, a good way to order them is what we call lexicographic order. Okay, so you order strings by increasing length, and when you take all the strings of length 35, you order them in alphabetical order. So it's not exactly the same as what you have in your phone book, or what you used to have in your phone book, because otherwise things don't quite work out. But it's morally the same. You just ordered the strings in some well-defined way, and you have an enumeration of all the strings that you can write. You get a countably infinite set. Now, the interesting thing for us is that this implies that all the programs, the collection of all the programs that you can write in your favorite programming language, no matter what it is a countably infinite set. Why? Because you write programs using a finite alphabet. The collection of all strings over that alphabet is countably infinite, and we are taking a subset of those, namely the legal programs, the ones that your compiler will appreciate, will accept, without giving you compilation errors. That's an infinite subset of a countably infinite set, so it must be countably infinite. Why? How can you figure out what the enumeration is? Well, the trick is simple. You take all of the strings over your alphabet. Take the first one. You feed it to the compiler for your favorite language, C++, minus, whatever that may be. The compiler says yes. Okay, that's a good program. You write it down. That's your first program. You go to the next string. You feed it to the compiler. If the compiler says no, that's not a good program, you throw it away. And you move on to the next one. You have an enumeration of all the strings. For each one of them, you ask the compiler, should I actually list it in the collection of all of my programs or not? If the compiler says yes, you list it. That way, you have a listing of all of the programs in your language by increasing length, if you wish. So that's the thing I want you to remember, because that's going to be important for answering our motivating question. The collection of programs that you can write in any programming language of today and of tomorrow is countably infinite. They can be put in correspondence with the natural numbers. But we wanted our programs to print out the decimal expansion of real numbers. So this naturally begs the question of what the size of the real numbers, the set of real numbers is. Is it countably infinite? Well, we don't need to guess, because our good old friend Georg Cantor, before going crazy, literally, he actually proved that the collection of real numbers is not countably infinite. You cannot put the real numbers in one-to-one bijective correspondence with the natural numbers. And this means you can't do it no matter how hard you try. In fact, what he also showed is that if you limit yourself to looking at the real numbers between 0 and 1, you still can't. The real numbers between 0 and 1, and actually there's nothing holy between 0 and 1. You could take any interval, which is non-trivial, that you care to mention. The number of real numbers, the set of real numbers in that interval, is not going to be countably infinite. So that's the bottom line. But what is even more beautiful, and for us computer scientists of fundamental importance, is how Cantor went about proving this result. And in fact, it's something that you can understand. I believe so. So let's see how he went about doing that. He introduced a proof technique which plays a fundamental role in computer science. And I can see there are people are really getting excited in the lecture room. I cannot see you at home, but I can sense the excitement from there too. Well, actually, I'm making these things up, but it's just to pump myself a little bit. Okay, so how does this proof technique, which is called diagonalization, work? It works in 2 steps. It's a proof by contradiction. Cantor started by assuming that the set of real numbers between 0 and 1 is countably infinite. That is to say, you can enumerate them, you can put them in correspondence with the natural numbers. And from this assumption, using this beautiful proof technique that is called diagonalization, Cantor derived bullshit, a contradiction, which means that his original assumption was false. So how did he do it? That's how he did it. And now, ladies and gentlemen, spider sense is tingling, because your life is not going to be the same after this. So, have you ever seen diagonalization before? If you haven't, or even if you have, spider sense is tingling, you will see it other times. So how did we say Cantor proved that the real numbers between 0 and 1? Actually, we are going to focus, just for the sake of argument, about what is called the open interval. All the numbers between 0 and 1, not including 0 and 1. So this is how this is typically written. This would be an interval which includes 0 but not 1, and you take all the real numbers in between. It doesn't really matter what we focus on. Okay, so what was the first step in Cantor's argument? That's step number 1. He said, assume the real numbers in this interval here can be enumerated. That is to say, you can list them all. You can take the first one, then the second one, then the third one. So let's do it. And since these are numbers between 0 and 1, I will just write what followed the 0 point. So the infinite, the infinite decimal expansion. I was getting so excited here that I was getting bogged down in. Okay, so let's write it. So let's assume that, so here we have the first number, and the first number starts at 0. So we start counting from 0. So you have the second number, here you have the third number. And let's assume that the first number is something like 0 point. So I just write the point. And then we have 1, 2, 3, 4, 5, 3, 2, 0, 1, 0, 0, 1, blah, 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 infinitely many. The second number is 0.34, please help me, 5, 7, 8, 9, 9, 0, 3, 0, 0, blah, blah, blah. And the third number is 0.8, 4, 7, 1, 1, 1, 0, 1, 0, 1, 0, 1, blah, blah, blah. And I stop here. So what is it that we have? We have an infinite array with infinitely many rows and infinitely many columns. Because these are all these are decimal expansions. And this goes to infinity, I mean, down there and so on. And of course, I've just written some numbers here instead of writing symbols. It doesn't really matter what numbers I write there, because the important thing is the second step in the proof. So let's assume that actually we have this enumeration of the decimal expansions of all the real numbers between 0 and 1. You know what Cantor did next? He constructed a real number between 0 and 1 that cannot be in this list, contradicting the assumption that this was the list of all the real numbers between 0 and 1. And you know how he did it? By going the diagonal way. Okay, so this is an array. So he started by looking at the first entry in the first row of this array. And he said, that's a 1. So my number will start 0.2. Okay? If my number starts 0.2, I've already made it different from the first number in the enumeration. Now I want to make it different from the second number in the enumeration. So what do? I look at the entry at position 2, 2, the second column, the second row. It's a 4. So I will write a 1. Then I look at the third row. So the number that I have so far is different from both the first number in the enumeration, because it differs from it in the first digit after the decimal point. It's different from the second number because it differs from it in the second digit. Question? The question is, it doesn't matter what number you put there, but just has to be different. Absolutely. So the rule that I'm going to follow is, if the number in the enumeration is a 1 there, I write a 2. If it doesn't have a 1 there, I write a 1. But you could choose whatever rule you like instead. I just cannot count up to 3, so that's sort of 1 and 2 are good enough for me. And we are computer scientists, so we are binary. So that's why I'm following this rule. But excellent point, absolutely. So I want to make now the number that I'm writing different from the third one in the enumeration. So I look at the third number after the decimal point. That's position 3, 3 in my infinite array. It's a 1, so I write a 2. And I keep going like this. The number that I will eventually write by following the rule, the nth number here, so let me call this number B, the nth digit of B will be 1 or 2. It's 1 if the nth column of the nth row of this infinite array was not 1, like in this case. And instead it's going to be 2 if the nth row of the nth column in the infinite array is a 1, like in this case. So this number that I write by following this convention is going to be an infinite sequence of 1s and 2s that doesn't appear in the array. It's not equal to the first element of the first number in the array because it differs from it in the first position. It's not equal to the second number because it differs from it in the second position. It's not going to be the third one because it differs from it certainly in the third position. And it's not the nth one, no matter what n is, because it differs from it in the nth position after the decimal point. Bingo. I've constructed a number which is not in this enumeration, contradicting my assumption that I had listed all of the real numbers. So my original assumption was bullshit. The real numbers cannot be listed. That was a knockout punch for me. Now, to come to grips with this type of argument, the best thing to do is to think about it at home and to do the exercises. Here, the important thing is, actually, the important things are two. First of all, the message. The message is the real numbers are not countably infinite. And not just all of the real numbers, even the ones between 0 and 1. Second message, the beauty of the proof technique. It's so simple that we can teach it in 5 minutes. Still, people, when they saw it the first time, they committed ritual seppuku, karakiri. This looks so weird in the 19th century. But in fact, today, everybody can understand it, even I. And this proof technique is called diagonalization. It works as follows. You assume that this collection of real numbers can be enumerated. Under this assumption, you show how you construct a number which is not in the list, contradicting the assumption. And the proof technique is called diagonalization because to construct this number, we travel down the diagonal of an array. It happens to be an infinite array, by so be it. You can write a program. For all I, you construct the ith digit in your new number by proceeding as follows. Look at the position ii in the array. If that is a 1, write a 2 at position bi of your number. If it's not a 1, so if it's a 1, you write a 2. If it's not a 1, you write a 1. 2 lines of code, depending on how you count the lines. We can even make it 1 line of code. Well, 0 lines of code, that's more complicated. It's an algorithm. Travel down the diagonal of your array, spit out something which is not there. So far, so good? For some, I'm sure. Okay, so this is the pictorial. Oh, by the way, just in case, just to prevention is better than curing, some people sometimes ask me at this point, yeah, but why can't you use the same argument to show that the set of rational numbers is uncountable? Because you could do exactly the same thing. You assume that the rational numbers can be enumerated, and then you travel down the diagonal, and you build a number which is not in the list. Well, the catch is the following, that the number that we've just constructed is not going to be rational. So it's going to be outside the collection of rational numbers, because the rational numbers have this property that their decimal expansion is eventually periodic. So stuff keeps repeating itself. Whereas here we are following a rule that is not going to lead to anything periodic at all. So just in case you were wondering, probably nobody was, but there you are. Okay, that's a picture of what we just seen. You can look at it at home, but that's exactly what we just done, more slowly on our scratchpad paper, digital paper. Now, you know, we can put everything together and complete the answer and complete our recipe, the answer to our motivating question. Remember our motivating question. If you don't, you can consult your visual memory because it's there on the slide. Suppose you have a computer with an unbounded amount of memory, an ideal computer. Can you program this computer to spit out the decimal expansion of any real number of your choice? Now, the answer is no way. You can't do it now. You will never be able to do it, where never really means never. No matter what programming language you use, no matter how much memory you're going to have, because we are going to assume, we have assumed that we have unbounded memory. You cannot get any bigger than that. And there is a fundamental reason why you cannot do it, is because the programs, the number of programs, is way smaller than the number of real numbers. Why? Because the collection of programs is countably infinite. You can enumerate your programs, but the collection of real numbers, the stuff you want your program to print out, is not. It's countably infinite. The vast majority of real numbers cannot be computed. Now, if you're philosophically minded, you may wonder, okay, but why do we have to take this calculus course where people talk about real numbers and they don't know what they're talking about? Because in reality, that stuff does not exist. Now, my engineering friends will kill me metaphorically when they hear that. But in reality, if you take the computer science viewpoint, most of the stuff that you see on this fantastic real line that you draw is not there for a computer scientist because you can't compute it. In fact, actually, it's not there because this thing that looks continuous is actually very discrete. As we all know, because the pixels here are lots of them, but not infinitely many. They are finitely many, only lots. But let's not get philosophical. Let's just take it at face value. You cannot compute all of the real numbers. And you know, have you ever heard of Alan Turing? I'm sure you have. And if you haven't, you should go and watch the talks that are recorded on the SES YouTube channel of the series of talks that we had in 2012, wow, 3 years ago now, for the Turing year. Well, he actually proved this stuff, amongst many, in 1936, long before computers were actually taking our jobs. So there you are. If somebody at a party asks you, yeah, but tell me, can all the real numbers be computed? Now you can entertain them with a long conversation over a glass of your favorite drink and your favorite food, and tell them, show them how cool you are, in case they needed any convincing. Eh? I do, but you probably don't. But now, you know, Dr. X, when I showed him this stuff, he actually said, okay, Luca, now we know that there are at least two orders of infinity. There is countably infinite, and there is the collection of the real numbers that is uncountable. It's not countably infinite. This is already a bit of a stretch because, I mean, in natural language, when you say, okay, either something is finite or it's infinite, and if it's infinite, wow, everything is the same. Well, we already know that's not true. Is it possible that there are more orders of infinity than these two? And you know what? Cantor did it for us. He showed us that there are infinitely many orders of infinity. And you actually also showed us how you can jump from one order of infinity to another one by using an operation that you all know and love from elementary school, discrete maths 1, whatever you prefer. And it's called the power set. Okay, so if you have a set S, then the power set of S is the collection of all subsets of that set. Is this new stuff? It shouldn't be. We already know that if you're looking at a finite set with n elements, then the power set of S has how many elements? Okay, I don't want you to guess. I'm giving you a piece of scratch pad. So suppose that, for instance, I have a set with 2 elements. That's my set S. What is in the power set of S? It's the set of all subsets of S. So it includes what? What is the smallest subset of S? The empty set. You put nothing in there. What is the biggest? Well, it's the whole of S. And what is in between? You can either put A and not B, or B and not A. So how many elements are in there? 4. From 2 to 4. Okay? If instead we go from n, we go to 2 to the n. Why? Because this is the collection of bit strings. And for every element, you can decide, do I put it or not? If you put it, you put a 1. If you don't put it, you put a 0 in your bit string. There are 2 to the n of those. And n is always smaller than 2 to the n. Yeah, but these are finite sets. We've already seen that in the infinite, things can turn out to be very different. Well, in this case, actually, they don't. Even in the infinite case, if you take S, then the set of all subsets of S is going to be bigger. So, for instance, if you take the set of natural numbers, you take the power set, the set of all subsets of the set of natural numbers. Let me write this for the cardinality. That's smaller than this. That's the set of all subsets of the natural numbers, which is smaller than the set of all subsets of that set, which is smaller than, you keep going. Every time you take the power set of what you had before, you get bigger and bigger and bigger and bigger. And in fact, you can do it with anything. You can do it with the reals, with whatever set you can start from, provided it's infinite. Get bigger and bigger and bigger. So there are infinitely many orders of infinity going up to mind-boggling size, assuming that infinite in itself was not mind-boggling already. Okay, now I don't need spider senses to figure out that either people are confused, or they're bored and confused, or any combination of those adjectives and more. Hello? If you're bored, I think I cannot do very much more to keep you awake than what I'm already doing. If you're confused, perhaps I can help. Yes, question. I was waiting for one.
What is the power set of S if S is only containing the empty?
Oh, that's a good question. So your colleague is saying, all questions are good, but this, so what is the power set of the empty set? I think that's the question. Or, okay, so the power set of the empty set is actually a set with one element, namely the empty set. It's the set that contains the empty set. Because this is the set of all subsets of the empty set. There is actually one, the empty set itself. And you can see the rule actually holds, because you go to 0 elements to 2 to the 0 elements, that is 1. Excellent. Thank you. Okay, but you can read more about this stuff. I'm not going to go through the proof. This is. Let me show you a useful trick. Well, it's not actually a trick, but it's a proof technique that you can use to show when two sets are of equal cardinality. The definition says two sets have the same cardinality if you can find a bijection between the two of them. For instance, I can find a bijection, I'm pretty sure, between mobile phones and people in this room. Well, I hope it's a bijection, unless some of you have 2 mobile phones with you. Otherwise, it's not a bijection anymore. But I'm assuming, which is in today's world is not probably a safe assumption to make, that each one of you has only 1 mobile phone. That's a bijection. However, sometimes constructing a bijection may be tricky. Well, again, Cantor to the rescue, together with 2 pals of his, Schroeder and Bernstein. This is a very German subject, in case you were wondering. Even though today it's not very German, it's very Israeli. Or, well, not just. Okay, so the theorem says, and it's a theorem that I'm not going to prove because the proof is way beyond this course, but it's a tool that you can use instead of establishing bijection, unless I ask you explicitly to establish a bijection, in which case you can't use it. So instead of establishing a bijection, you can do the following thing. You can establish 2 injective functions, one from A to B and the other one from B to A. If you can do that, then this theorem says there is a bijection. But you can invoke the theorem to argue that the 2 sets have the same cardinality. For example, suppose that I want to show that the collection of all finite subsets of the set of natural numbers is countably infinite. Note, finite subsets, not all subsets. I said before, if you apply power set, you become bigger in terms of cardinality. So that would be impossible. However, if you restrict yourself to the set of all finite subsets of the natural numbers, then you get a countably infinite set. How do you establish this fact? Well, it's easier to establish 2 injections than a bijection. Or at least I'm making it easier. So let's focus on an injection between the natural numbers and the collection of finite subsets of the natural numbers. This is easy. Why? Well, because your colleagues here in the room are going to do it for you now. And you're also doing it at home, I'm sure. So I want you to give me a function f that takes as input a natural number and spits out a finite subset of the natural numbers. And this should be an injective function. How are we going to do it? Using the KISS method. Keep it simple, Schroeder. Because we're using the Cantor-Bernstein-Schroeder theorem. So keep it simple, Schroeder. Okay? You take as input n. You want to spit out a set. Let's make it related to n. What is the simplest set that you can build from n? The set that only contains n. Fantastic. That's a finite set. It only has 1 element. And moreover, is it an injective function that we've defined? Okay, if you take the number 3 and the number 35, is f of 3 different from f of 35? Sure. Why? Because f of 3 is the set that only contains 3. F of 35 is the set that only contains 35. And this has got absolutely nothing to do, and these 2 sets are different, by the way. Last time we looked at them. Because 2 sets are equal if they have the same elements. And this has got nothing to do with the fact that I was looking at 3 and 35. If you take 2 different natural numbers, you will get different sets when you apply f to them. Okay, so that's an injection. The one in the opposite direction is trickier. And I encourage you to think about it at home. How can we actually construct a function g that takes as input a finite set of natural numbers and spits out a natural number that somehow corresponds in a unique way to the input set? Hint: cryptography. You encode the set that you get as input as a number. And that's my daughter. Okay, so I think I'm being told from my phone that perhaps this is time to call this call the end to this lecture. And in fact, it's also 13:54. So I'm even on time. Exercise, work on this function at leisure. And I encourage you to have a beer as you go along, if you like beer, or a glass of wine, because it's going to inspire you. Thank you.